Every time I leave you, girl, he's the one that's near you, girl. Even as I drive away, I can hear the words you say.
Alright, we're on to section 5.2, and in 5.2 we're going to look at the standard form of a quadratic function. Now, last time we looked at quadratic functions, but we didn't look at standard form. We looked at general form. I don't think I used that term, but last time we looked at y equals ax squared plus bx plus c. We said any function that could be written in that form is an example of a quadratic function, and if it is written in this form, it's called general form. But it can still be a quadratic function and not be written in that form. It could be written in this form right here. This is called standard form. So this form that I've highlighted right now, this form could be switched into general form, and that's why it's still considered a quadratic function. But this is standard form, and we love this form. We specifically love this form when we're graphing, because this form here allows us to find the vertex very, very easily. With general form, the one we did last time, there is some things you can figure out by looking at general form. You can figure out whether the parabola is facing up or down very quickly, for example. But if you want to find the vertex, it takes a little bit of work. With standard form, though, you can figure it out very, very quickly, and that's what we're going to show you here. So let's start actually by graphing the most basic of all parabolas. Here it is right here, y equals x squared. And as I've probably already told you, what I call this, and I'm not the only one, but what I call this is the mother function. The mother function, okay? It's the most basic parabola of them all. So let's graph this, and since we don't know how to graph yet, let's do the form graph in the method that always works, and that is a table of values. So we'll put x and y. And let's use some values like -3, -2, -1, 0, 1, 2, and 3. Okay, so we're going to put -3 into x. So that means -3 squared, all of it squared. -3 squared is 9. -2 squared is 4. -1 squared is 1. 0 squared, well 0 times 0 is just 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. Okay, let's graph those. -3, 9 is up here. -2, 4. -1, 1. 0, 0. 1, 1. 2, 4. And 3, 9. And there you have it. We have that parabolic shape. It's hard for me to draw this, but I'll do the best I can. That side was okay, but this side's always harder. Yeah, that's pretty bad, but I'll go with it. So this is our most basic quadratic function. It's the mother function. You can now see why it has this parabolic shape, because when you square something, whether it's positive or negative, the answer is going to be positive. So -3 becomes 9, and 3 also becomes 9. That's why you get that symmetry, right? We have the axis of symmetry right down the y-axis in this case. So basically the equation for the mother function, y equals x squared, it's actually the same as this equation, but there's just a few extra parameters. There's this a, this h, and this k. Now if we wanted to make that the mother function, what would a have to be? A would have to be 1. What would h have to be? H would have to be 0. And what would k be? Also 0. Do you see what I mean? If I had a is 1, h is 0, and k is 0, I could eliminate some of the stuff. I don't need to put plus 0, I don't need to put the minus 0, and I don't even need to put the 1. So all I would have is y equals x squared. Oh, it would be the mother function. So the mother function is just the case where a equals 1, h equals 0, and k equals 0. But what happens if a doesn't equal 1, h doesn't equal 0, and k doesn't equal 0? In other words, what effect do these parameters, the a, the h, and the k, what do they do to the mother function? So that's what we're going to check out next. The first thing we're going to look for is the h. What does the h do to the mother function? So let's go to this. This is the mother function right here. And we're going to look at what the h does. So I'm going to move this slider. Right now h is 0, like we said. I'm going to move this slider, and we're going to see what happens as I change that number. So it's at 0. Let's change it to positive numbers, like positive 1, positive 2, and take a look at what's happening to the graph. To the parabola. Pretty obvious, right? When I'm at h equals 3, look where the vertex now is. It's not 0, 0 anymore, it's at 3, 0. Let's go back to the starting point. And I bet you can guess what's going to happen when I go make h negative. When I make h negative, it goes down to the left here. Let's go down to h equals -4, and you can see the vertex is now at -4, 0. So that's pretty easy to understand. Basically what the h parameter does is it moves the vertex, or in effect moves the whole parabola, to the left or right. So let's write that down. There we go. H shifts the parabola horizontally. So if positive, like if h is positive, it moves it to the right, and if negative, it moves it to the left. I hope that makes sense. If not, you can put it in your own word. And by the way, this is going to be a source of confusion later because of this minus sign here, but we'll talk about it after. Okay, let's figure out what the k value does. You might even be able to guess. So back here, we'll put this, yeah, everything's back to the mother function, and now we're going to move that k value. So let's see what happens. Oh, I already moved it there. As I move it up, now you might think the parabola is getting smaller, but is it getting smaller? No, all that's happening is it's moving up. You just can't see as much of it. So when k is 5, you can see that the vertex is now moved up to 0, 5. So let's go back down to the mother function when k equals 0, and you know what's going to happen. When I move k to the negative, the parabola moves downwards. Let's go down to the -3, and you can see that k equals -3, and that means the vertex is now at 0, -3. So what the k value does is it moves the parabola up and down. It moves it vertically. Let's write that down. There, k, it shifts the parabola vertically. Again, I will say if positive, so if k is positive, it moves the parabola up, and if k is negative, it moves the parabola down. Great, just one to go, the a. Now the a that actually does two things, so we'll do one at a time, but you won't be able to help but see both, I suppose. So let's take a and let's make it move it upwards. So we'll make it bigger and bigger positive numbers, and there you go. So actually you can see what happens, but I don't really want you to worry about that right now. What I want you to worry about is what happens when I get to 0 and negative. So you can see as long as it's positive, it's like that. When I get to 0, where to go? Do you know where it is? The line, because it's now a line, is right along the x-axis. Why is it a line? Because remember we said a can't equal 0. If a equals 0, let's go back here again. If a equals 0 in the general form, if a is 0, there's no x squareds. So it would just be bx plus c. Hey, that's a linear function. So that's why when you have a equals 0, it seems like it disappears. Really what's happening is it's just turning into a line. Anyway, so again, up to the positives, it's looking like this. When I go to a equals 0, it's now a line. Not so very interesting because it's not a parabola. How about when I go to the negatives? Boom. It's now facing downwards. Oh, it's the a value that impacts whether it faces up or faces down. Up when a is positive, down when a is negative. And do you remember I actually told you about that in the last video? I said you could look at the a value and it would tell you whether the parabola is facing up or down. So let's write that down. A impacts the orientation of the parabola. So let's say if positive, if a is positive, then the parabola faces up. If a is negative, then the parabola faces downwards like that. I hope my little code I'm using for all these is making sense. I know I could put this all in words, but I thought this might be faster. Okay, last one. Still the a, and I'm sure you noticed this. There's something else that happens with a. As a gets bigger and bigger and bigger, what's happening to the parabola? It's getting skinnier and skinnier and skinnier. And that'll just keep happening. As higher I go, it's skinnier it gets. Okay, let's go back to the mother function. That's when it's 1. So right here. What happens is I get smaller from 1. It gets wider and wider and wider and wider. Okay, wider until you get to the line. So we know that it's wide between 0 and 1. But it's still wide when I would do those first negative ones, right? That's still wider than the mother function. Still wider, still wider. When's it the same width as the mother function? When I get to -1, because the only difference between 1 and -1 is the negative sign, which is flipping it over. So this, if you take a look at the width of that, and then I'll go as quickly as possible, I'll make it go to +1, and you'll see it's the same. See how wide that is? Now look at, look at that. It should look about the same. Okay? Anyway, once you get to -1, that's congruent, we say, to the mother function. It's just facing downwards. And then as the a gets smaller and smaller and smaller, it gets narrower and narrower and narrower. So a also impacts the width of the parabola. Now this is a little bit harder to put in words here. If a is greater than 1 or a is less than -1, then you get a narrow parabola. So I'll just draw a really skinny parabola. But if a is between -1 and 1, so if it's between -1 and 1, then you get a wide parabola. Of course, if it's negative, it'd actually be facing down, and same with here. If it's negative, it'd be facing down. But the point I'm trying to make is, and maybe I'll actually write this in here, it's going to be narrow if a is bigger than 1, 1.5, 2, 17, or if a is less than -1, -1.3, -4, whatever. It'll be narrow. It's going to be wide when a is between -1 and 1. Remember, this is the same thing as this, -1 to 1, if it's between but not inclusive. What if it is 1 or is -1? So if a equals plus or minus 1, either positive 1 or -1, then it's congruent to mother function. Same width as the mother function. Alright, so that is important to know those parameters. You talk a lot about that in grade 12 as well, because the same sort of impacts that these parameters had, they do this for all the different graphs, all the mother functions. The cubic mother function or the absolute value mother function does the same sort of thing. So this is very, very important to learn, especially in grade 12. Alright, now we're going to learn how to actually graph parabolas. So you could use the table of values, but we'd like a faster method. So what you're going to do is find the vertex and the axis of symmetry. That'll be very quick using the standard form of the function. Then you're going to find 2 to 4 points just to one side of the vertex. We'll talk about y in a second. And then if you want, the book talks about finding the y-intercept and the x-intercept by setting x to 0 and setting y to 0. I think that it's usually a waste of time and often is more trouble than it's worth. But we can talk about that as well. So let's graph a few of these and we'll be done. So the first thing we want to do is we want to find the vertex of this. So let's remember here what these parameters do. So first of all, let's look at the k. Remember, this is the a value right here. This is the h value here. And this is the k value here. So the a value is what? It's -1. The k value, I skipped the h for a reason. The k value is what? It's 2. And the h value is what? You're all rolling your eyes and saying it's 3, obviously. It's not 3. I'm sorry. It's not 3. It's -3. What? Why is it -3? Well, if you go back and look at the equation of this form, it's a and then x minus h squared. So let me just write that up here just so we can keep referring to it. Y equals a x minus h squared plus k. So if I ended up with x plus 3 in here, h can't be 3. Because if I put 3 into that equation, right where the h is, if I put 3, I'd have x minus 3. And it doesn't say minus 3, it says plus 3. So h must be -3. How come? Because it's like x minus, and how much is my h value? -3. And is it not true that x take away -3 is x plus 3? Yes, it is true. So this is the tricky part that I have warned you about before about the h value, is it's always kind of the opposite of the way it looks. It says x plus 3, so the h is actually -3. Okay, you'll have to get used to that. Alright, well, what does that tell us about the vertex? Well, we know that if the h value is -3, remember what a negative h value does? It moves the vertex, or moves the whole parabola, 3 to the left. So rather than the vertex being here at 0, 0, it has to be 3 to the left. 1, 2, 3. But we also have a k value of 2, positive 2. What does that do? It moves it up 2, 1, 2. Here's our vertex right there. So basically, to get the vertex, take the opposite of the h value, or opposite of what it looks like. The h value really is -3. But take the opposite of what it looks like when you first look at this, which is -3. And then take this value, the k value, which is 2. So there's my vertex, -3, 2. Okay, next thing, does this thing face up or down? How do you know? You look at the a value. The a value is negative, so this thing's going to face down. Is it going to be wide or narrow or neither? It's going to be neither, right? This a value is -1, which means it's congruent to the mother function. So it's going to be the same width as the mother function. Okay, that's the first step, is to find the vertex and also the axis of symmetry. You don't need to draw the axis of symmetry, but just know that there's an axis of symmetry that's running right down through the vertex, right? But I'm not going to include that. I'm going to actually get rid of that. Okay, so the next thing it says to do is to use a table of values and to find just a few points. And it says to find them on one side of the vertex. So don't pick points like, maybe you like the point 2, so you decide you're going to put 2 into x. Why is that a bad idea? Because 2 is so far away from the vertex that it's probably going to be off the graph. Like if I try this, 2 plus 3 is 5, 5 squared is 25, put a negative on it, that's negative 25, plus 2 is negative 23. Yeah, there's no point in putting 2 in there. It's negative 23, it's way down here somewhere. So you want to pick points that are really, really close to the vertex. Since the vertex was at negative 3, you might want to pick the points like negative 2 and negative 1. Or you might want to pick on the other side of the vertex. You might want to pick the points negative 4 and negative 5. Why would it make no sense at all to pick the point negative 2 in here and negative 4? Why would that be silly to put negative 2 and negative 4 in here? Because of symmetry. Once you know what the point is for negative 2, it's going to be exactly the same for negative 4. Don't understand? I'll show you. Let's find these points. Let's put negative 2 in here. Negative 2 plus 3 is 1. Now I square it. 1 squared is 1, and then I put the negative on it. So I'll say that again. Negative 2 plus 3 is 1, 1 squared is 1, and negative 1 plus 2 is 1. Okay, let's do negative 1. Oh, let's graph that. Negative 2, 1. So that goes right here. Next, negative 1 plus 3 is 2. 2 squared is 4. Negative 4 plus 2 is negative 2. So negative 1, negative 2. Okay, this is at this point, just from symmetry, I know there's an axis of symmetry here. Since this is 1 over from the axis of symmetry, it has to be another point 1 over here. Since this is 2 over from the axis of symmetry, there has to be another point right over here. But if you didn't know that, you could definitely try negative 4. Negative 4 plus 3 is negative 1. 1 squared is still 1. Slap a negative on it, it's negative 1. Plus 2 is 1. We get the same values we did here. So there's no point in doing points on both sides of the parabola. Okay, you might want to do one more. Maybe you want to put 0 in here, which will be the y-intercept actually, so it's kind of nice. 0 plus 3 is 3, 3 squared is 9, negative 9 plus 2 is negative 7. So 0, negative 7, and then because of symmetry, we know this one as well. There we go. There is our downward facing parabola with vertex at negative 3, 2, and it has the same width as the mother function, and I'm sorry I drew it so poorly. Okay, now I want to show you one thing. I'm going to go back here and look at this graph we drew here. I want to show you that there's something called a step pattern. You could actually write in here if you want, or use step pattern, because that's what I'm going to teach you right now, this step pattern. A lot of people like this. What I want to show you is, once you have the vertex here, to get the next point, you could have moved over 1 and up 1. So up 1. Then you could have moved over 1 and up 1, 2, 3. Then you could have moved over 1 and up 1, 2, 3, 4, 5. Guess how much you'd move over? Well, 1. You always move over 1. Guess how much you'd move up this time? 7. Is that true? Is that going to work? Well, let's see. If I put 4 in here, 4 squared is 16. Is that 7 more? Absolutely. So this will work. Up over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7. This works as long as the a value is 1. So let's make sure it worked here. Say we found the vertex very quickly, negative 3, 2, so we put that there. And then we see the a value is negative 1. So we know it faces downwards, and it's congruent to the mother function. Oh, I can use a step pattern. I go over 1 and down 1, since it's facing down. Over 1 and down 3, 1, 2, 3, yep. Over 1 and down 5, 1, 2, 3, 4, 5, yep, it worked. Over 1 and down 7 doesn't fit, I'm finished. Great! So that's a wonderful way as well to get the other points. But what happens when you don't have an a value of 1? What happens if you have an a value of 2? Let's see if we can figure that out in the next question. So here we go. Let's find the vertex first of all. So we're going faster for every one of these. Vertex, take the opposite of this number, so negative 1, and then take the k value, negative 3. Vertex is at negative 1, negative 3. Now I'm going to pick some points that are close. So I'll show you how to do this first of all without using the step pattern. Pick some points that are close to negative 1. So I would pick either 0 and 1, or I could pick on the other side negative 2 and negative 3. But I like 0 and positive numbers, so I'll pick the right hand side here. Alright, throw 0 in here. 0 plus 1 is 1, 1 squared is still 1, 2 times 1 is 2, take away 3 is negative 1. So 0, negative 1 is 1 point. And because of symmetry, this is also a point. Put 1 in there. 1 plus 1 is 2, 2 squared is 4, 2 times 4 is 8, and 8 minus 3 is 5. So 1, 5 is a point. And because of symmetry, this is a point. You can try putting another point, but I don't think it'll fit. 2 plus 1 is 3, 3 squared is 9, 2 times 9 is 18, take away 3 is 15. Didn't fit. So we're done. This is all the points we can see. So we'd expect with a positive a value that it would face upwards, and this one does face upwards. And because the a value is greater than 1, we'd expect a narrow parabola. And this is a narrow parabola. It's narrower than the other function, so it's looking good. Okay, how would I have done that without using the table of values? How could I use a step pattern? Well, let's take a look at the difference between the points this time. The vertex was at negative 1, 3, right? So once I got the vertex, I would have had to go over 1, and not up 1, I would have gone up 2. And then I went over 1, and I went up 1, 2, 3, 4, 5, 6. And then I go over 1, and you can see here, I'd go up 10. So what's going on here? Usually I went over 1 and up 1, and then 3, and then 5. This time I went over 1 and then up 2, and then 6, and then 10. What's the difference? Twice as much. Since the a value is 2, you're going to multiply all those numbers by 2. So let me show you again. Vertex is at negative 1, negative 3. So I put a dot at the vertex. Then because the a value is 2, I don't go over 1 and up 1, I go over 1 and up 2, twice as much. Then I go over 1 and not up 3 like normal, I go over twice as much, I go up 6. Then I go over 1 again, you always go over 1, but then I don't go up 5, I go up 10, so I'd go way up here, right? Like that. That's how that works. So that's the thing that makes it a little bit more difficult with step pattern, but usually a lot of people figure that out and use that instead of the table of values. I don't care which one you use. Moving on, let's do another one, vertex of this. Interesting, what's the vertex? Well, the opposite of what the x value looks like is negative 2. What's the k value? I don't see anything there. Well, that means the k value is 0. So my vertex is at negative 2, 0. This thing face up or down? Up, because it's got a positive a value, and it's between 0 and 1. So what does that mean? It's going to be a wide parabola. I'll do this both ways again. X, y. So let's pick some values close to negative 2, maybe negative 1 and 0 and 1. Negative 1 plus 2 is 1. 1 squared is still 1, and half of 1 is a half. 0 plus 2 is 2. 2 squared is 4, and half of 4 is 2. 1 plus 2 is 3. 3 squared is 9, and half of 9 is 4.5. Let's do this first of all. Negative 1 and 1 half. 0 and 2. 1 and 4.5. We can probably get another one in there. Let's do 2. 2 plus 2 is 4. 4 squared is 16, and half of 16 is 8. And I don't think we'll get any more than that. There you go. Because of symmetry, we know this point, we know this point, we know this point, and we know this point. There's nothing wrong with this. You don't have to use the step pattern. I'm totally okay if you use this. Do it this way. But notice how I didn't just get a couple points. I got as many points as I could find that fit in the on the grid. I think that's important. I'm going to be more strict about that this year. Okay, if you want to use the step pattern, find the vertex. There it is. Usually you go over 1 and up 1, but because this is a half here, you'd go over 1 and up a half. Then you go over 1 again, always go over 1, and instead of going up 3, go up 1 and a half, 1 and a half. Then you go over 1, and instead of going up 5, go up half of 5 is 2 and a half, 1, 2 and a half. Then go over 1, instead of going up 7, go up half of that, which is 3 and a half. Half, 1, 2, 3, 3 and a half. See, it works every time. Last one, the vertex of this one. This number here, is that an H or is that a K? That's a K. So we know the vertex is at something 9. What's the H value here? It's 0. There's no number in brackets there, so it's 0. So 0, 9 right here. Does it face up or down? Faces down. And look at the A value is negative 1. So it's going to be similar to the congruent to the mother function. I'm just going to do step pattern. I'm going to go over 1, down 1. Over 1, down 3. 1, 2, 3. Over 1, down 5. 1, 2, 3, 4, 5. Over 1, down 7. 1, 2, 3, 4, 5, 6, 7. Next would be over 1, down 9. Doesn't fit, so I'm finished. With symmetry, I can fill these points in. See how fast this is? And I'm finished. Good luck to me trying to draw this. but that's good. This is not quite as good, but I'm going to keep it. Of course, if you wanted to, I'm not going to, but you could fill in some table of values. I'd probably pick the numbers 1, 2, 3 or something like that. I think 4 fits in there as well. Fill those in and you'll get these points right here. Alright, that's it. That is how you graph parabolas, quadratic functions, when you have it in standard form. We love standard form.